Hello, I'm Jordan Kelly, and this is Dylan Moberly, and we're Team Hot Air Balloon, and this is our analysis of a motor mount.
Okay, so we're from the hot air balloon senior design team, and here's the rig that we used in that project. So what we needed was a mount that would connect the motor to the fan end piece that you see in that picture there. And the purpose of this motor is to power a fan that will supply excess air to simulate real hot air balloon conditions.
So this is the first iteration of the motor mount. The basic idea is a square platform supported by a thin rod, and the end of the rod is threaded in order to screw into the fan end piece. The dimensions here are shown. The square is 12 by 12 inches with a quarter-inch thickness, and the rod is a 0.5-inch diameter. And on the right are the CAD models and the motor placed on one of them. Okay, so this was the free body diagrams for the FEAA analysis. The first one done is using a fixed geometry condition on the threaded end of the rod, and a distributed load of 50 pounds to simulate the weight of the motor and fan assembly. And the second one is the same boundary condition of the fixed geometry on the thread, but with a 170 Newton force pushing against the front face of the platform. This is simulates the act of the flow pushing against the mount when it exits the duct.
Okay, so here's the second iteration, and we wanted to improve upon the first iteration by adding more supports that the stress and the force could be distributed through. And here's a free body diagram. And so it's the same basic setup as before, but now the fixture's on the outer ring. And iteration 3 is basically just a different arrangement of iteration 2. The supports are in different places. And again, the free body diagrams are essentially the same as iteration 2.
These are the final results of the analyses we ran. The first analysis we ran was the static analysis using the distributed load to simulate the weight of the motor and fan assembly. In the results for that section, none of the pieces yielded, and all of the max displacements were much less than an inch, and the buckling loads under that condition did not yield at all. In fact, it was very safe under buckling. For the second static analysis we ran, we used the force to simulate the effect of the flow exiting the duct, pushing on the motor mount. And in that case, the first iteration yielded and had a max displacement of over an inch, which is very high. And for the second and third iteration, it did not fail, however, and the displacements are relatively low. And finally, we ran a modal analysis since it's next to a motor, which will send a lot of vibrational forces through the piece, but none of the resonant frequencies were close to what the motor would be operating at.
Okay, and so to cap off this presentation, we compared the experimental results that we found in SolidWorks simulation to the results from our calculations using strength of materials calculations, and the results can be seen here. There's a notable error, but this can be largely attributed to the fact that we had to simplify the boundary conditions when performing our calculations to make the calculations feasible.
Thank you.